Okay, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to everybody. So we will look into another properties of Fourier series, which is symmetric. So we will look into the symmetrical characteristic of our predict signal. Okay, so that this consideration is take place so that we can simplify our calculation when we want to determine our Fourier series coefficient. So there are three consideration of symmetrical characteristic, which are first we have even symmetric, odd symmetric, and half symmetric. Okay, so you have even symmetric. Oh, so you have even symmetric, and then you have odd symmetric, and then you have half wave symmetric. So for even symmetric, you have xt equal to x minus t over here. I must meet this equation. So you have original xt. When you inverse your original xt will be equal to your xt. So this is even symmetric. Okay, any signal that meet this equation over here or condition over here, so we call it is even symmetric. Okay, so for odd symmetric over here, so your original signal and then you inverse your original signal, and then after that your inverse its polarity by multiplying with negative, so you will get back your original signal. This kind of signal that meet with this condition, we call it odd symmetric signal. Okay, for half wave symmetric, okay, so you have the original over here, and then you do this transformation where you shift your signal by t and a half, which is half wave, half cycle, okay, of your total cycle t. Okay, so you shift by t over 2. Okay, and then after that your negative multiply with negative, so you will get back your original signal. Okay, see, it's almost the same thing as odd symmetric, but this one we uh, what we call it, we don't do inverse, but this one is we just shift, and after that we multiply with negative. Okay, so you move shift by t and a half, and then after that we multiply with negative, we will get back our signal. So let's go one by one. Okay, so first we take a look for even symmetric signal of our predict signal. So if we have even symmetric signal, if you look the graph over here, so this is the graph. So this is our predict signal, and then if we see over here, so if you look over here, so we have even symmetric signal. Okay, when you inverse your signal, you will get back your original signal over here. So if you have even signal like this, so your a naught will be equal to 0, your an equal to 0. So so your an is not equal to 0, your an is not equal to 0, but your bn equal to 0. So that means you no need to calculate your bn because it's equal to 0. So what you need to do is just need to calculate your a naught and a n. So it's much more simpler than by knowing this, because you do not need to calculate your bn for even symmetric signal. Okay, so let's do for odd symmetric signal. So like over here, so here is one example of odd symmetric signal. If you look over here, okay, so what you need to do is, if you have this kind of signal, okay, which is odd symmetric signal, so your a naught value will be equal to 0, so your an value will be equal to 0, but your bn is not equal to 0. Okay, so in this case, so you do not need to calculate your a naught and an anymore, because based on this symmetrical characteristic, you know already your a naught will be equal to 0 and your an will be equal to 0. So what you need to do is just to calculate your bn over here using the formula. Okay, so much faster and is must simplify in we have simplify the calculation. Okay, because we know already our a naught a and an is equal to 0 for odd symmetric signal. Okay, so let's go for half wave symmetric. So over here, as I see, the xt equal to minus x t minus t naught over 2. Okay, so if you look over here, so you have a periodic signal over here. Okay, so you have one cycle will be this one, so 0 to t. This is one cycle. Okay, and then when you move it by half, so for example, this is your original signal, and then goes to transformation where you shift by half of the cycle. So this one will be moved to here. Okay, and then after that you multiply with negative, so you will go up here, so you will get the original signal over here. Okay, so this is half wave symmetric, okay, signal. Okay, for this signal, so your n naught will be equal to 0. Okay, and then for an equal to 0 for n odd value, an is not equal to 0 for n odd value, but an is equal to 0 for n even value. Same goes to bn. So your bn will not equal to 0 for n odd, and then is equal to 0 for n even value. Okay, alright. So this characteristic is very important so that we can simplify our calculation. Okay, so as a conclusion over here, so you can see, okay, in this table, so if you have even a symmetric signal, so your n naught will not be equal to 0, an is not will be equal to 0, so you need to calculate your n naught and an, but bn is equal to 0. You can skip this. Okay, so you know already your bn will be equal to 0. Okay, for odd symmetric signal, so your n naught will be equal to 0, an will be equal to 0, but your bn will not be equal to 0, so you need to calculate your bn. Okay, so for the last one over here, for half wave symmetric, so your n naught will be equal to 0, and then this one a to n, b to m represent even number of n even number, which is equal to 0, but this one represent an odd number which is not equal to 0, that you need to calculate the coefficient. Okay, so this is so you must look into your periodic signal in terms of the symmetric characteristic, whether your signal will be fall into even symmetric, odd symmetric, and half symmetric, and then you can simplify it. Okay, the calculation to find the Fourier series coefficient based on this table over here. So your calculation will be more simple, and you can get the answer much more faster. Okay, alright. Hopefully you understand about this symmetrical characteristic. Okay, and then thank you for watching. Okay, bye.